Alright, reaction mechanisms. I got 10 minutes before your class starts, so I should be able to get through this, right? Yeah, why not? Reaction mechanisms are kind of a unique beast on the AP exam. They don't require any calculator, however, they sometimes appear in a calculator section. And the way you go about doing them is different depending on which book you use. Our book is going to have a completely different method than the book than what you're about to see here. However, this apparently is the easiest concept. I haven't seen the other two, so this is how I know how to do it. But you're welcome to read the text and figure it out for yourself. Reaction mechanisms are simply a blow-by-blow description of what's going on in the system that's causing you to produce your products. And it's not necessarily, since we can't see down to the molecular level, it's more of an educated guess. It's a hypothesis on what is going on to either make a bond or break it. Now, it has to. There are a couple things that must always go on. It has to agree with our has to agree with every experiment we've done. So if we've come up with a rate constant, which is where you usually see these, we'll come up with a rate constant and it'll say, this is the proposed rate constant and here's the reaction mechanism. Does that agree? It has to agree with your rate constant, and it has to agree with, not with your rate constant. It has to agree with your experimentally determined rate law, and it has to agree with the overall stoichiometry of the reaction. And I put those in bold, that it must agree with the stoichiometry, even though I haven't seen any that have yet to disagree with the stoichiometry. But they must agree with the stoichiometry, and they must agree with the experimentally determined rate law. And anytime you are asked to justify why you either think a reaction mechanism is true or whether or not a reaction mechanism is false, you will always probably use the word experimentally determined rate law in there somewhere. Now, each step in a reaction mechanism is called an elementary step. And they read kind of like a recipe. You have to finish this step before you can do the next step, before you can go on to the next one. And they come in a couple of different flavors based on their molecularity, which is simply the number of molecules that participate in that reaction. So it's your reactants. If something is unimolecular, such as if A simply goes to being product, so it involves just one reactant, that's typically like a decomposition. So that means that A was most likely unstable to begin with. Something can also be bimolecular, meaning that two molecules collide to produce your products, or two of the same molecule can collide. You can also see it written instead of just A plus A, you could see it as 2A becomes this. So if a coefficient of 2, that would make this bimolecular. That tripped me up when I did it the first time. And the last type that we're going to go on about, but you will rarely see it, is if it's termolecular, like tertiary, meaning 3. So either 3 different reactants or 2 of one and 1 of another come together to collide to produce your products. This is extremely rare. And we'll never see 4, we'll never see quadramolecular, because while 3 is extremely rare, 4 is almost unheard of, and we won't go into those. You probably won't go into those until you're either a sophomore or junior in college if you're a chemistry major, and if you're just a biology major, pre-med, or in engineering, whatever it is you want to do, you may never see this again. So those are the 3 types, and I definitely suggest you know the word molecularity because it will come up in a lot of free response questions, easy essay questions that talk about the molecularity of a certain equation. So just to review, put this all into a table. If something is unimolecular, it's just a product, just a reactant decomposes into a product. And the rate expression for that would simply be the rate constant times the concentration of A or whatever it is your reactant is. Bimolecular, you can have 2 flavors. You can have something smacks into itself or something smacks into something else. If it smacks into itself, then it's going to be squared, its concentration squared, so it'll be second order in this case. Otherwise, it's going to be to the first. And termolar, again, it is extremely rare, and the rate constant would equal whatever you have 2 of, you'll square that, that will be the second order, and the other thing will be first order. So if I have 2a plus b, the rate equals k times a squared times the concentration of b to the first. However, you cannot predict the rate expression from the overall stoichiometry. I can't take a reaction of a plus b gives me c and then use that to determine the rate expression. I have to use the elementary steps that I'm given. The rate expression of an elementary step is given by the product of the rate constant and the concentration of the reactants in each individual step. And we're going to later look at putting them together to come up with the overall rate constant, or the overall rate expression for a reaction. Now, the more molecules you have, the more collisions you'll have. So the physical state of each rate expression also matters, and it'll tell us whether that reaction is fast or slow often. And all elementary steps, their rate laws can be written from their molecularity. So you can look at 2a plus b and say, oh, that means that a is second order. Again, you can't do that with the overall stoichiometry of a problem. So here we have a reaction of hydrogen plus nitric oxide producing nitrogen gas and water. And we're given a possible mechanism. We're asked, what is the molecularity of each of the 3 steps? So first off, let's look at this one up here. We have 2 of the same things colliding to produce 1 new product. So 2 into 1 means that that's bimolecular. Next, we have N2O2, dinitrogen dioxide, colliding with a hydrogen molecule to produce a new product. 2 things coming together, that again is bimolecular. And in the final step, dinitrogen monoxide collides with hydrogen. 2 things coming together, once again, bimolecular. So for all 3 of these elementary steps, we are bimolecular. Let's talk about some of this now. Let's keep adding to our key terms. You see how N2O2, dinitrogen dioxide, is produced and then immediately used up in the next step. That means that N2O2, dinitrogen dioxide, is what we call an intermediary. So an intermediate is used as soon as it's formed. So we can pretty much cross it out because it's not going to be part of a final product. It's used here. Sorry, it's formed there, and it's used in the immediate step. We have another one here. If we look, N2O2, dinitrogen monoxide, is produced and then immediately consumed in the following step. So we can cross that out as well. If we say had a catalyst, though, a catalyst will look similar to an intermediate. And the fact that it will actually cancel out, it will be on both sides of the equation, except it is used and then produced. So if we had a catalyst here, let's say that element A is a catalyst, it would be a product, it would be a reactant at the beginning, like that, and then possibly show up in the next reaction, but it would end up before you finished or even at the finish, exiting the system. Like so. So an intermediate is formed and then used immediately, and a catalyst is added and then leaves. And the AP exam loves to ask which is identify your intermediates, identify your catalyst. Just make sure you can keep track that while A would cancel out on both sides of the equation, it would cancel out, it is a catalyst because it's added and then leaves. Now, everything that's left over you can add, and I'm putting up my air quotes even though you're not here to see it, you can add up on either side, and it should be the same as what you have in your stoichiometry above, in your balanced chemical reaction. So if I take everything that's left, I would have two NOs, and I would have 2 hydrogens producing 1 N2 and 2 waters. That's a capital O. There we go. And if I check, sure enough, that is the balanced chemical reaction above. So this is a actual possible mechanism for the above reaction. Oh, and I just realized I made a bit of a mistake. So on first glance, these would look, no, these are bimolecular. I'm sorry. I didn't make a mistake. I'm right. These are bimolecular. If you cancel out the intermediaries, though, you could say this was unimolecular. You'd be wrong because the actual individual step is bimolecular. So reactions and mechanisms, because this is all going to tie back to the rate expression, the K rate, or rate equals K times the concentration. The rate is still going to be determined experimentally. You always have to determine the rate experimentally. It's the only way it can be done. The rate of the overall reaction, however, is limited by a combination of the rates of the elementary steps. And it is limited by the slowest step in the mechanism. So if you've watched the I Love Lucy video that I posted before this, the rate at which candies could be put into their boxes, or sorry, the rate at which candies could be finished was limited by Lucy and Ethel because they were the slowest step. They were the rate determining step. They determined how quickly that conveyor belt should have been able to go, or at least in an efficient system they would have. However, as you saw, that was not the case for them. So a reaction is limited by its rate determining step, the slowest step. So if we were to write the reaction expression for something, we would stop after the slowest step, because the slowest step is going to ultimately determine the rate of the reaction. So if we're given all this information, we're told we have a balanced chemical reaction for the production of nitrogen dioxide and fluorine, or for whatever that big thing is. This experimentally determined the rate law was the rate equals K, that it was second order overall, first order with relation to nitrogen dioxide, and first order with relation to fluorine. And we have a suggested mechanism. Typically you'll see this as the last question on a free response, and they say, is this an acceptable mechanism? They'll give you the mechanism after you've calculated the rate and probably a K value, and they say, is this an acceptable mechanism and why? So, first off, we're told that this first step, we've got a nitrogen dioxide and it slams into a fluorine and produces that big thing and fluorine. That fluorine then goes on to slam into another nitrogen dioxide to produce more of whatever that other thing is. So that means that fluorine, we can immediately say, fluorine, you, sir, are an intermediary. I can cross you out. You don't count. And that first collision is really slow to happen. But that second one goes really fast. Well, what is limiting this reaction? The slowest step. This is the Ethel and Lucy of the reaction. So it's going to limit it. So we can draw a line and we're going to ignore everything that's below it when it comes to writing our rate expression. Because the rate expression is dependent upon the slowest step. So we do everything up to the slowest step. Everything up to and through the slowest step. So I'm going to draw a line and I'll write the rate expression for just the slowest, or for everything up to the slowest step. So I would get that the rate equals K times the concentration of NO2 to the first, because there's only one of them, and F2 to the first, because again there's only one of them. And does that equal the experimentally determined rate law? It does. So this is a valid mechanism. And I would state that in my free response.